Alright, hello everyone. So we're going to talk about dependent events with conditional probability. So we've already talked about independent versus dependent. So we already wrote down the formulas for us from the previous lesson. So we have probability of A and B is equal to the probability of A times the probability of B. Okay, and dependent events, that is the probability of A and B, would equal the probability of A times the probability of B given A. Okay, remember this big little bar, or redundant or weird thing to say right there. That bar there means given. Okay, so notice here I've underlined the P of B given A is the probability of B occurring given that A has already occurred. Okay, now conditional probability of an event is the probability that one event will happen if it is known that another event has definitely happened. Okay, so what we're going to do is we're going to rearrange the multiplication rule, this one right here, the one I have in purple, so that we can talk about conditional probability. So we have probability of A and B equals the probability of A times the probability of B given A. Alright, I made a mistake earlier, so sorry if you can't see that. Just pause and look at it for a little bit. Okay, alright, so what I'm going to do is I'm going to divide both sides by the probability of A. Okay, so now those eliminate. So now I have a new formula, okay? Because sometimes we don't know the given probability, that little fancy one, the new little guy that we were talking about. So now we have that the probability of B given A is equal to the probability of A and B over the probability of A. So now we have this new formula. Yes, you will have to remember it. Okay, so again, if I need to find out the probability of an event given something has already happened, it'll be the probability of those events happening together divided by the first event. So just A. Alright. Why does this formula make sense? Great question. Everybody wants to know. When we know something's happened, that changes the sample space. Okay, so I'm going to use the highlighting and shading that we've been looking at with Venn diagrams. So specifically, it shrinks the given event, shrinks to the given event. So we know that A has already occurred. So that becomes our sample space. So if you remember, okay, there's A, all right? So A has already occurred, okay? That's my new sample space, okay? Then for B to occur, it has to occur with A. Okay, so that was like the double shading that we've been talking about. Okay, for B to occur, it has to occur with A. Alright, well, in the only spot where B occurs with A is that intersection. Okay. So, we now have that formula, okay? So now if we take these colors and kind of apply it to our formula, and there is a typo right here. Quickly, just, gosh, I'm trying to grab something quick. I'm going to grab the Sharpie. This should be the probability of B given A. That's a formula, remember? So we have the A and B. Well, A and B, that was that double intersection that we have here that I've highlighted in blue. So that, and I'm just using my highlighter to continue with the color coding because I know you guys love the color coding. A and B divided by probability of A. Okay. So then we could take out, you know, when we only want B happens given A. All right. Okay. All right. Moving on. So let's put this into play. All right. So we got some eye color and hair color. All right. Nice big table. So if we select a woman and find that she has brown hair, what is the probability that she will also have hazel eyes? All right. So what we're looking at is the probability that we have hazel eyes given, so again we have that bar to represent given, brown hair. Okay, that's the probability that we're looking at. So that's what we're trying to solve for. Okay. So if we were to set up our formula, okay, we have two things that we want to look for. Okay, you know, right here, the probability of both items and the probability of the given item. So the probability of both, okay, that's one item, and the probability of the given item. Well, the given item here is brown hair. Okay. All right. So now let's find those items using the table. So that both happens. So hazel eyes, brown hair. Hazel eyes and brown hair. 29. So that's 29 out of the big total. So that's 313. So 29 out of 313. And then we have brown hair. Okay, so that's just all the brown hair. So brown hair is 143 out of the 313. Okay, so what we have to do now is set up our formula. Okay, so we have the probability of both over the probability of brown hair. Okay, so that's going to be the probability of both. What we said is 29 over 313. Probability of brown hair, 143 over 313. And then just like back in math land, this would just be a keep, change, flip. But what happens is that the 313s will eliminate each other. So then all we have left is 29 over 143. Okay? So you can also do this with the table if you have it. Okay? You're not guaranteed that you can do this all the time, but if you have it, you can use it. So the probability of 29 over 143 should kind of look familiar. So the probability of brown hair, that is this row right here. If you notice, 143, 143. And then if we go to the hazel eye column, choop, you have that 29. 29 out of 143. Okay, so that's where that number comes from. So your sample space is just the brown hair and then the one column of hazel. So you do 29 out of 143. If you have the table, you can do that. If you don't, you have to use the formula. So, looking at letter B. If we select a woman and find that she has brown eyes, what is the probability that she also has black hair? All right. So what we're looking at, and I am going to do some abbreviation. So, because I'm running out of room. So brown, I'm going to say is BR. And black is going to be BL. Okay. And I'll make this a capital L since we have that bar to worry about. Okay. So the probability of black hair given brown eyes, that's what we're looking for. Okay. The probability of both is one item, and the probability of brown is our other item. Okay. So, why do I feel like I spelled brown wrong? Ugh, it's one of those moments. Alright, anyway. So the probability of both items occurring is going to be 36 out of 313. The probability of brown eyes occurring, okay, that's going to be the 122 out of 313. So then we can set up our formula. And I'm going to push it over here since I've kind of made it cramped over here. So that's going to be 36 out of 313, all divided by 122 over 313. Continuing to simplify, that's going to do a keep change flip, which is really nice, is that the 313s will eliminate each other, so we have 36 over 122. Okay. Ugh, my work is a little chaotic. But, like I said before, we can use the table to kind of help us out. So, our given item is the brown eyes. Okay, so we can go look at brown eyes. Well, that's this column here. So I'm making orange like the limited sample space. Okay, and we want to know that she has black hair. Well, looky, looky, looky. 36. Okay, so 36 out of 122. Okay, so our sample space is 122, and then in that individual sample space we have 36 people have the brown eyes and black hair. Okay, so again, if you have the table, you can use that. Otherwise, you can just do this formula. All right. So we can prove independence, just like we could prove mutually exclusive events and all that jazz. All right, so if we draw two cards with replacement, I don't remember what highlighter I've been using, but with replacement, we know that those events are independent. Because again, it doesn't affect in between trials. Okay, with replacement, we're just putting things back in. Nothing is changing from our total population. Now, if we have without replacement, meaning I'm keeping the card out or I'm keeping the marbles out of the bag, okay, that's affecting everybody's probability, so it's becoming dependent. Okay. Now, in the real world, it can be difficult to determine if two events are independent or dependent. We do have a way to prove independence, however, it's going to be using these formulas. Okay, so we have the probability of A and B equals the probability of A times the probability of B. Hey, that should look familiar. Okay. And then we also have the probability of B given A is equal to the probability of B. Okay. So you can use either one of these formulas to prove independence. Okay. Either one is fine. Alright. So we just have this table and then we'll be done. Oh no. I'm going to have to make another video. Alright. I'm going to have you guys do this one by yourself, but we'll do this one together. Alright, so what we're going to do is we're going to have blueberries and fresh independence. So we are going to do probability of blue given, and fresh.